All right, today we're going to do something really cool. We are cracking open the code behind the single most common type of transaction in Bitcoin's history. I mean, this is the OG, the fundamental architecture that started it all.
You've seen them, right? Everywhere. Those Bitcoin addresses that start with the number 1. Now, they kind of just look like a random jumble of letters and numbers, but each one is basically the front door to a digital safe. So, what's the combination? Well, that's exactly what we're here to find out. So, that digital safe has a name. It's called Pay-to-Public-Key-Hash, or P2PKH for short. You can think of it as the original blueprint for how to send and receive Bitcoin. Seriously, it's the bedrock of simple payments all across the network, even today. Okay, so right off the bat, here's the first really clever twist. You might think you're sending Bitcoin directly to someone's public key, but you're not. Nope, you're actually sending it to a hash of their public key. Think of it like a cryptographic shadow. And this little extra step, it is absolutely crucial. Let me show you why. So this journey has 2 main steps. First, you start with the full public key. That key gets put through the SHA-256 hashing algorithm. But we're not done. That result gets hashed again, this time using something called Rippium D160. And what comes out the other side is a much shorter, way more manageable string of data that we call the public key hash. Okay, so why bother with all that? Why the extra step? Well, the payoff is huge, and it's twofold. First, and this is pretty straightforward, using the hash makes Bitcoin addresses shorter and just easier to deal with. But here's the big one, the more important reason. It adds this extra layer of security. Your actual public key stays hidden, totally private, until the exact moment you go to spend the funds. Until then, only its shadow is visible on the blockchain. Pretty cool, right? Okay, so we've sent our Bitcoin to this public key hash. How is it actually locked up and secured? Well, this is where we meet what's called the locking script, or script pub key. The best way to think about this is as the set of rules, the exact combination required to open our digital safe. And this is the lock itself. I know, it looks like some cryptic old-school computer code, but each of these OP commands is just a super simple instruction. When you put them all together, they form this brilliant little security test that anyone, and I mean anyone trying to spend the Bitcoin, has to pass perfectly. So every lock needs a key, right? Well, in Bitcoin, that key is another little piece of code. It's called the unlocking script, or script sig. This is the part that you, the spender, provide to prove you have the right to open that lock. And what's just amazing is how simple this key really is. I mean, look at it. It only has 2 things in it: a digital signature that you create with your private key, and your full original public key. That's it. So we have our lock, we have our key. Now let's see how they actually fit together. All right, it is time for the moment of truth. The Bitcoin network is about to take our 2-part key and our 4-part lock and run them together. This is like the final exam. Let's walk through it step by step and see what happens. First things first, the network uses this temporary workspace called the stack. The easiest way to picture it is like a stack of plates. You can only add stuff to the top or take stuff off from the top. The process kicks off with the unlocking script. It places your signature and then your public key right onto the stack. Okay, now the locking script jumps into action. Its very first command is op-dupe. That's just short for duplicate. And it does exactly what it sounds like. It makes a copy of whatever is on top of the stack, which in this case is your public key. Next up is op-160. The script grabs that new copy of your public key and runs it through that exact same 2-step hashing process we talked about earlier. And the results? It's hash, which now gets placed right on top of the stack. Okay, so now the script needs something to compare that new hash against, right? So it pushes the expected public key hash, that's the one the Bitcoin was originally locked to, onto the top of the stack. So now you've got 2 hashes sitting right there, side by side, ready for the first big test. And that brings us to the first critical test, op=verify. This command looks at those top 2 hashes and asks one simple question: do they match? If they don't, boom, the script fails right there, transaction over. But if they do match, that means the public key you provided is the correct one. The check passes, and both of those hashes get popped off the stack. We are now at the final command, op-checksig. This is the ultimate proof of ownership. It takes the signature and the public key and does some crypto magic to mathematically verify that the owner of the private key authorized this exact transaction.
If that signature is valid, it replaces both items on the stack with one single, beautiful result. True. And there you have it. With that final true sitting all alone on the stack, the script execution is complete and successful. The digital safe is open, the transaction is valid, the Bitcoin can now be spent. Every single check has passed. So that's the elegant logic of the original Bitcoin transaction. It's so cool, right? But this whole foundational idea of a programmable locking script, well, that was just the beginning. The system was actually designed from day one to evolve. And over the years, new address types have been built right on top of this foundation. You know those addresses starting with a 3? They introduced something called pay-to-script hash, which lets you lock up funds with way more complex rules, like needing multiple signatures to spend. And then even more recently, we got the BC1 addresses for SegWit, which made transactions smaller and cheaper, really improving the whole network's efficiency. So what's the really crucial takeaway here? It's this. Bitcoin security isn't just one static, unchangeable thing like a physical vault. It's actually a flexible, programmable language. P2PKH was like the Hello World program that proved a totally new kind of digital ownership was possible, all enforced by pure logic and code. And that leaves us with a really fascinating question, doesn't it? If this elegant, multi-step verification process is what Bitcoin's simplest script can do, what else is possible?